Welcome to the Introduction to Industrial Control Systems, or ICS Networks, and Operational Technology, or OT Networks course. It's recommended that you watch this course before taking the 4Scout for OT Security 101 course. It's important to note you will only receive credit for this lesson if you fully complete this video. Also, we recommend viewing this video in full screen mode. This course contains 5 lessons. In the first lesson, we'll cover the history of industrial automation and control systems. In the second lesson, we'll discuss modern-day ICS environments. In the third lesson, we'll cover the Purdue reference architecture. In the fourth lesson, we'll go over the different device types found at each level of the Purdue model. And in the fifth lesson, we'll explain the difference between IT and OT networks. In Lesson 1, we'll cover a brief history of industrial automation and control systems. Industrial automation and control systems have revolutionized manufacturing goods and the management of processes. From rudimentary mechanical contraptions to the interconnected systems that choreograph modern production lines, the evolution of these systems is a testament to human ingenuity and the relentless pursuit of efficiency. The earliest instances of industrial automation trace back to the mechanical looms of the 18th century. The most notable of these was the Jacquard loom, invented by Joseph Marie Jacquard in 1801, which employed punched cards to automate the pattern weaving process. This innovation not only reduced manual labor, but also enabled complex designs that were previously unattainable. As the Industrial Revolution progressed, engineers continued to seek ways to enhance productivity and reliability. The introduction of electrical engineering in the 19th century gave rise to the development of the first electric motors, leading to increasingly autonomous machinery. The early 20th century marked a significant milestone with the popularization of the assembly line by Henry Ford, which standardized the mass production process. Each step set the foundation for today's sophisticated systems, where advanced computer algorithms and robotics often exert control, integral to industries worldwide. During the Industrial Revolution, the so-called Mechanical Revolution spurred machine-based manufacturing, marking a distinct shift from handmade to machine-forged products. Innovations such as the steam engine significantly boosted production capacity and efficiency. In this era, mechanization replaced manual labor, with machines taking over repetitive and strenuous tasks. This transition laid the groundwork for modern industrial automation, demonstrating the benefits of mechanical assistance in production processes. As mechanical systems became more complex, engineers started incorporating basic control mechanisms to ensure precision and safety. These ranged from simple governors on steam engines to regulate speed, to more sophisticated systems designed to coordinate the movements of different machine parts. This era represented a significant step in how humans utilize machinery for labor, paving the way for subsequent electronic and digital automation systems. In Lesson 2, we'll cover the ICS environments of today. An industrial control system, or ICS for short, is a system that manages or oversees an industrial process. For example, it could be a factory that produces cars, an electricity grid, or an entire city's transportation system. Each of these scenarios is managed by an industrial control system. An ICS network might be restricted to a single factory or even a specific production line, but it can also extend across multiple geographical locations. Different methods of ICS architectures are employed to control varied physical systems, which we will explore further in this course. Industrial control systems can operate by themselves using control loops. They have different degrees of autonomy and are usually supervised by operators, who can modify the processes based on measurements and feedback obtained from the system. The first ICS architecture we will discuss is SCADA, which stands for Supervisory Control and Data Acquisition. SCADA is an architecture that monitors and controls a large physical process using a central server. the SCADA server. Usually, SCADA architectures rely on centralized controllers, which make decisions to adjust the various processes based on data collected from these controllers. The remote field controllers have less control over the process, and their main function is to acquire and pass along the data that is used to make decisions. In general, this architecture tends to use open protocols, which makes it very flexible when using field devices from several different vendors. The SCADA architecture is typically used in wide geographical areas, such as power transmission, or a distribution grid, which can spread throughout an entire country. The second ICS architecture is DCS, which stands for Distributed Control System. A DCS uses control loops that are distributed across the physical system, enabling most processes to be carried out autonomously. Unlike SCADA architectures, a DCS typically exhibits less control at the centralized location, with most of the control functions being performed by the field controllers. Vendors of distributed control systems often offer complete solutions encompassing controllers, servers, human-machine interfaces, and engineering workstations. This means that it can be challenging to have a multi-vendor DCS environment. Typically, a DCS is found within a more confined area, such as a single plant or factory, where it manages manufacturing processes like in a car factory or a chemical plant. It's important to understand that most of the protocols commonly used in an ICS network were developed many years ago. These protocols are very different from the standard IT protocols, such as HTTP and FTP. When these protocols were developed, computer security was not a big concern. Back then, ICS systems were completely isolated, and having physical security was sufficient. Many of these protocols also didn't run on Ethernet. Most of them ran over serial technologies. To accommodate the advancement of communication technologies, most of these protocols are now encapsulated within the TCP/IP stack, enabling them to function on Ethernet. There are two main types of ICS protocols. Open specification protocols used by SCADA systems have openly available documentation and interoperability between devices from different vendors. And proprietary protocols used by distributed control systems are developed by specific vendors, typically for exclusive systems. In Lesson 3, we'll cover the Purdue reference architecture. The Purdue reference model was developed by the Purdue University Consortium for Computer Integrated Manufacturing in the 1990s and was standardized by the International Society of Automation as ISA-99. Today, it serves as a reference model in IEC 62443, a security standard for control systems. The model employs the concept of zones to subdivide an enterprise and an ICS network into logical segments, each consisting of different systems, playing a similar role in the network. The components executing OT control functions, such as opening valves and activating pumps, occupy the lower levels of the Purdue model, while those executing IT functions, such as user authentication and software patching, are located at the upper levels. The primary purpose of the Purdue reference model is to establish a secure architecture for an ICS environment. Best practices advocate for controlled and limited communication from the upper levels of the model down to the control networks at the lower levels. This separation facilitates the establishment of strict access control rules, thereby contributing to a more secure environment. In Lesson 4, we'll cover the different device types found in each level of the Purdue model. The field devices are located at the lowest level of the Purdue model, level 0. They provide a direct interface between the ICS network and the processes. They are the actual devices in an ICS network performing mechanical operations. There are two types of field devices, input and output. Input devices are used for measuring pressure, temperature, or other similar physical quantities. And output devices like valves, switch breakers, or turbines can directly manipulate a process. The next Purdue level is level 1, which contains the field controllers. These controllers are usually located near the field devices and are physically connected to them. They receive input data from field devices, process this data, and then send the resulting information to output field devices. There are different field controller types used by the different industry and ICS environment types. The first type of field controller is a PLC, which is short for Programmable Logic Controller. A PLC is a computing device used for the automation of electromechanical processes. Typically, a PLC can be found in close proximity locations such as factories or plants, mostly manufacturing ones, where it controls machinery. The next type of field controller is an RTU, which is short for Remote Terminal Unit. The primary function of an RTU is to interface the SCADA servers with the physical field devices. RTUs are typically used in geographically distant areas, such as small substations for energy grids. Purdue Level 2 is the supervisory control network. The devices in this layer are primarily tasked with supervising, monitoring, and controlling various processes. This is where the SCADA systems and distributed control systems, which we discussed earlier, are located. The SCADA and DCS servers display the data acquired by the field controllers, and operators use them to manipulate and control various processes. Purdue Level 3 is where the IT side of an ICS network begins. Systems that manage the control plant operations are found in Level 3, such as DNS servers, DHCP servers, domain controllers, and NTP servers. The final Purdue level, Level 4, houses IT systems that manage business-related activities. These services, systems, and applications are typically managed and operated by the IT organization. Let's summarize a standard workflow in a process governed by an ICS environment. We begin with a field device, such as a gauge that measures physical quantities. This input device then sends these measured details to a field controller, such as a PLC. The field controller, in this case the PLC, then forwards these measurements to a device at Level 2, for instance, an HMI, or human-machine interface. Using an HMI, an operator can monitor the process and make necessary adjustments. For example, based on measurements received from a gauge, a field controller, like an RTU, could alter a field device by either opening or closing a valve. These changes by the RTU are then relayed to the SCADA server. Each stage of this communication chain introduces security vulnerabilities within the ICS network. In the final lesson, we'll explain the differences between IT networks and OT networks. To understand the value proposition of Forest Scout for OT security, it's important to understand the differences between IT and OT networks. First, as a reminder from Lesson 2, an industrial control system supervises and governs industrial processes, such as a car manufacturing unit, an electricity grid, or a city's transportation system. An ICS network can be confined to a single factory or spread across various geographical locations. Different types of ICS possess varying degrees of autonomy, though they are typically overseen by human operators who can modify processes based on collected measurements and feedback. Next, we'll be discussing OT, or operational technology, a term synonymous with industrial control systems. Let's start by discussing the characteristics of an IT network. First, think about a large national forest, which contains many trees. Because trees drop seeds, more trees are naturally added in random places. There's no actual plan for how all the new trees evolve. For management purposes, forest rangers need to determine methods to bound the forest. Also, not all trees are the same. For instance, a spruce tree might be located next to an elm tree. Similarly, IT networks typically have many elements, such as different types of devices and applications. New devices and applications are often added by users without IT approval. In fact, quite often IT knows nothing about these added elements. This is how a BYOD, or Bring Your Own Device environment, operates. It can be quite a challenge for IT to define the boundaries of the environment for management purposes, while also allowing users to run their required business services. This creates an ongoing challenge for IT to define what standard or normal behavior is and to control users going in and out of the environment. Finally, with IT environments, throughput and confidentiality are of paramount importance. Next, we'll discuss the characteristics of an OT network. Think about a private, well-manicured garden. A garden is a purpose-built environment in which there are fewer trees, typically arranged in neat lines. It usually contains a wide variety of trees, bushes, grass, and flowers, but these elements are set in a very defined layout. Additionally, the garden boundary can easily be walled off with fencing and gates. In the same way, an OT network would be purpose-built and engineered to have long-lasting processes without disruptions. Devices are not expected to connect or disconnect from the OT network without the knowledge of an administrator. Additionally, typically, there aren't a lot of new devices connecting to the OT network. If a PLC is controlling a process today, it is likely to be controlling that process tomorrow, the day after, and so on. Similarly, the number of applications or functions in use is smaller and more static. The applications in use today are likely to be the ones in use tomorrow, and so on. These factors make it easier to define what the normal behavior of an OT network should be. Furthermore, in an OT network, the traffic is fixed and the throughput is low. Finally, the most important attributes of OT networks are control, availability, and integrity. Thank you for watching the Introduction to ICS and OT Networks course. You can now take the knowledge check for this course.